Welcome everybody. So the last video I went over what quantum numbers were, and I left you off having to try and figure out what the quantum numbers were for the fourth energy level. And so remember, each quantum number, it helps describe the location of an electron in an atom. So we have the first quantum number, the energy level, over here. We have the next quantum number, the sublevel here. The next quantum number, the orbital, and then the spin of the electron within the orbital. Each one of these quantum numbers helps us locate where an electron is in an atom. So when I look at the fourth energy level, I have my energy level, number 4. I then have my sublevels, 0, 1, 2, and 3. I then have my orbitals. So for S, the orbital can be plus or minus L. So that would just be 0. For P, it would be -1, 0, and 1. For D, it would be -2, -1, 0, 1, and 2. And for F, it would be -3, -2, -1, 0, 1, 2, 3. If we count up all the electrons in 4, we would have for each box 2 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and this can hold 32 electrons. Now, why do we care about this, and how can we tie this to what's actually going on in the atom? Well, when we try and look at the electrons in an atom, we need to be able to arrange them. If we understand how the electrons are arranged in an atom, we can understand the reactivity of the element. And that's going to be our big theme. Once we understand how electrons are arranged in the atom, well, how does that help them be arranged in the periodic table? When we know how they're arranged in the periodic table, well, how does that help us understand how they react in nature? So how do electrons fill up in an atom? Well, they use this rule called the diagonal rule. And they fill up based on the energy that each orbital has. You'll always fill up orbitals with the lowest amount of energy first. In German, this is called the Aufbau Principle. Aufbau means order. So if we look at this, the first energy level to fill up and sublevel to fill up, an orbital to fill up is 1s. After 1s fills up, 2s will fill up. After 2s fills up, 2p and 3s will fill up. After 3s fills up, 3p and 4s fills up. After 4s fills up, we go back to 3d, then 4p, then 5s. And we can keep going, but you can see here, this is how the energy relates to this. The lowest energy orbital is the 1s orbital. The next higher up energy level is 2 and the sublevel s, so the 2s orbitals. The next sublevel within 2 is 2p, and that contains 3 orbitals. So if we go back to our diagonal rule, 1s, 1s, 2s, 2s, 2p, 2p, 3s, 3s, and so on. So the diagonal rule, it relates to the energy of the orbitals and the sublevels. Now remember, when we look back at this here, if we have the sublevels, S, P, D, and F, S has 1 orbital. It can hold 2 electrons. P has 3 orbitals. It can hold 6 electrons. D has 5 orbitals. It can hold 10 electrons. F has 7 orbitals. They can hold 14 electrons. There are G sublevels and H sublevels and I, but we don't have enough electrons in the current atoms that we've discovered to fill those up. So we generally don't talk about them. Now, let's go through and try and write electron configurations. These are the first 18 atoms in order. So for example, hydrogen, it has 1 electron. Helium has 2 electrons. Lithium has 3 electrons, and so on. Hydrogen only has 1 electron. Let's go back to the diagonal rule. The first electron sublevel and orbital to fill up is 1s. So we show that by writing this, 1s and 1. This top number here, this shows you the number of electrons. This is called an electron configuration. The next element, helium. Remember, we're going to go in order. The next one, and the same one, is 1s. That can hold up to 2 electrons. 1s2. Now, s is completely filled. So we look at our diagonal rule. 1s can fit up to 2. Then we're going to go to 2s. 3 electrons. 1s2. That's 2 electrons. 2s1. That's our third electron. Beryllium, 4 electrons. 1s2, 2s. I can put 2 in there. I have a total of 4 electrons. Boron, 5 electrons. 1s2, 2s2. Now 2s is filled up. What comes next? 2p. 2p1. Carbon, 6 electrons. 1s2, 2s2, 2p2. So what I'd like you to do is I'd like you to go through up to argon. We'll go over it together. Now, let's look at how to fill up the electrons with orbital diagrams and talk about something called Hunds Rule. If we look at boron, it has 5 electrons. Carbon, 6 electrons. Nitrogen, 7 electrons. Oxygen, 8 electrons. Fluorine, 9 electrons. Neon, 10 electrons. So boron's 5 electrons. 1s2, 2s2, that's 4, 2p1. This is called an orbital diagram. This shows how the electrons are actually inside the orbitals. Let's say I were to go to 6 electrons. 1s2, 2s2, 2p2. Watch this. 2p1, 2p2. This is very important. With nitrogen, I do 7. 1, 2, 3, 4, 5, 6, 7. Again, very important. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Very important. Now, I keep saying very important, but I'm not telling you why it's important. This is called Hunds Rule. What Hunds Rule says, and I think I wrote it here, electrons will occupy individual orbitals before pairing with each other to minimize repulsions. This happens in a sublevel with multiple orbitals. So this happens in P, this happens in D, this happens in F. It doesn't happen in S. So go ahead and fill out fluorine and neon. So this is showing you the orbital diagrams. This is following Hunds Rule. One last thing that you have to be aware of, if you've noticed, in each of the orbitals, I always put opposite spins. And this is because of the Pauli exclusion principle. No 2 electrons can be like this. This is wrong. You can't have it where the two electrons in the same orbital have the same spin. It is not allowed. And that's because, let's say that this was a p orbital, a 2p orbital here. So this is 1, 2, 3, 4. This is 2p4. Let's look at the quantum numbers for each of these electrons in here. N, L, Ml, Ms. These both have an N for 2. 2, 2, 2, and 2. They all have 2. These have an L for P, which is 1, 1, 1, and 1. These all have an Ml for -1, -1, 0, and 1. And their MS's, since they're spinning up, would be 1/2 and 1/2. 1/2 and 1/2. What you'll notice is that these two electrons here have the same 4 quantum numbers. That is not allowed. Wolfgang Pauli said that they have to have opposite spins in the same atom. You can't have two electrons with the same spin in the same orbital. That's what you can translate this to. So you cannot have two electrons in the same orbital with the same spin. It's not allowed. Now, we did this whole thing on quantum numbers, right? We spent time on, well, let's use quantum numbers and like, why are they important? Each electron is assigned 4 quantum numbers in the atom. The quantum numbers, again, tell you where you are most likely to find an electron. That is why we use the quantum numbers. No two electrons can have the same 4 quantum numbers. That's the Pauli exclusion principle. A question on a test, and we'll do some of these in class, what are the 4 quantum numbers of this electron in an atom? And you have to define them. That's how we generally use the quantum numbers. Another question, what are acceptable quantum numbers? And I'll give you choices. We'll practice this all together when we have the double period. Now, when you get to atoms that are really large, it's sort of annoying to write out the entire electron configuration. So you can use the nearest noble gas, which is group 18 on the periodic table, to represent what's known as the core electrons. This saves a lot of space. So the core is the electron configuration of the noble gas, and then you put on the extra electrons. So something like beryllium, it has 4 electrons. If I look up at the periodic table, helium has 2 electrons. So I can save myself some time by writing He 2s2. Now, you don't really see it very much with beryllium, but imagine something like calcium. If I wrote out the complete configuration of calcium, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. If I look on the periodic table at the nearest noble gas to calcium that comes before it, it is argon, Ar. Argon has 18 electrons. Those 18 electrons are these. So I would put those 18 electrons as argon and then add on the extra electrons that represent the outer electrons, not part of the core. Now we haven't done like how many electrons are in each atom, so as we do that and we go back to this in the next few days, I think it will make more sense. They do this for group 3 as well and show you what that looks like. Now one of my favorite things to do is to use the periodic table when I'm doing electron configurations. I feel like it makes things a lot easier for me to use the periodic table. The diagonal rule is great. Remember, the diagonal rule looks like this. If I just zoom in here, we can write it 1s, 2s, 3s, 4s, 5s. I can go to 7, but I'm just going to, for time and space, 2p, 3p, 4p, 5p, 3d, 4d, 5d, 4f, 5f, like this. The diagonal rule, now when I fill this in here, 1s fills in first, 2s fills in next, 2p, 3s in terms of energy, 3p, 4s, 3d, and so on like this. Now, I can use the periodic table, though, alongside that. There are different blocks on the periodic table. The first one is the S block. S block is groups 1 and 2. The next block is the D block, groups 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And the next block is the P block, 13, 14, 15, 16, 17, 18. Down here is the F block. If you count, there will be 14 boxes for the 14 electrons. Going across are the periods. So period 1, period 2, period 3, and so on. 4, 5, 6, 7. What this allows me to do is it allows me to know where to stop when I'm making an electron configuration. Let's say, for example, I wanted to do phosphorus. Phosphorus has 15 electrons. When I look on the periodic table, phosphorus is in group 15 and period 3. So phosphorus is right here. Group 15, period 3. So that means that phosphorus is going to go as follows: 3p1, 3p2, 3p3. Phosphorus's last electron is going to be 3p3. That helps me to know where to stop. Now I can backtrack. Before 3p3 came 3s, so 3s2. Before 3s2 came 2p6, so I put 2p6. Before 2p came 2s, so 2s2. And before 2s came 1s, so 1s2. This is my configuration. So it allows me to know where I stopped and work backwards, or if I know where I stop, I know where to end. 1s2, 2s2, 2p, 1s2, 2s2, 2p6, 3s2, 3p3. It gives me, a way to use the diagonal rule or not use the diagonal rule and hopefully do electron configurations quicker. It depends on what you want to do. Now, if we tie this back to quantum numbers, and then I'm going to stop here. If we tie this back to quantum numbers, if I look at 3p has the three orbitals. P has 3 orbitals. 1, 2, 3. Let's see, what are the 4 quantum numbers of this electron? Well, I know it's in n equals 3 because it's the 3rd energy level. I know the L is P, which is 1 always. I know the ML could be -1, 0, or 1, and my electron's in 1. And I know that the MS is 1/2 because it's in the up spin like this. Here are my 4 quantum numbers. Those 4 quantum numbers, they tell me the most probable location of finding an electron in this particular atom. No 4 quantum numbers of 2 different electrons in the same atom can be the same Pauli exclusion principle. Notice I follow Hunds Rule. I put them all in 3 separate orbitals. When I go through, I keep all these things in mind. Now I'm going to stop here. Next time I will review this. I'll go over shapes of orbitals and we'll talk about the rest of the chapter. Thanks so much.